Hey folks, for our final installment of the gravitation and planetary motion unit, we're going to take a look at now what happens once we start applying that gravitational attraction that exists between two objects. And to begin, we're going to kind of branch off from the universal law of gravitation and consider one of Isaac Newton's thought experiments known as the cannon or Newton's mountain is what it is referred to as. The setup on this thought experiment that he had was, what if we put a cannon on a really, really, really high mountain? Not like Everest high, but higher. Like, what if we were able to put a cannon up there, and how fast would we need to fire that cannon to ensure that the projectile that comes out of it is going to go all the way around the planet and hit the person who fired the cannon in the back of the head? That was what the theory was. So he set out to figure out, well, how do the laws of gravitational attraction apply here? How does that elicit what we can see in terms of motion, where an object will continuously move around the planet without ever coming back down? So thinking of the idea of orbit, right? How fast would it have to be to stay in orbit was the question that he was essentially asking. So if we take a look at this little applet here that I have, so this Newton's cannon, right? So this is from ionaphysics.org. Here's the mountain, here's the earth, and basically what we can do here is we can modify how fast this is being fired, and we can see approximately how far the object would travel before it gets pulled back down to the earth. If we don't fire it fast enough, like right there at 4,000 meters per second, it doesn't make it very far around. If we move the speed up a little bit more, right, let's go like 5,500 meters per second, right, we see that it's not moving fast enough, so it gets pulled inward. We start to see some of the circular motion ideas come back here. If it's not moving fast enough, that means it's being pulled too much, it's not going to maintain that true circular path. So if we go much faster, right, we see that we can escape as opposed to orbit. And if we slow it down a little bit more, right, so we slow it down, same thing, right? So there's really this fine range that on the surface of Earth ends up being right around that 7,000-ish meters per second. Here we go a little bit faster, right? So or slower, we can start seeing that curvature coming back down, and how modifying the speeds is going to make a difference here, right? So this is going to orbit because we see it fully turning back, but its orbital path is going to be much longer than we would expect it to be. Still going to get back. It's still going to hit that person in the back of the head, but we can get much, much, much closer as we go around the globe here, right? So there's a 6,800, doesn't quite work. So we'll go to 7,000. And just that slight difference lets it go much, much, much further around the globe. Here's a 7,100, right? So you can really see what's happening in terms of the speed as it goes and how it can maintain almost a near perfect circular orbit depending on how fast you get it to move. So, right, we can actually figure out, based on a little bit of circular motion, what's going to happen there. But for objects that are in orbit, right, the term weightlessness comes up. Notice the quotes around weightlessness. When you're in orbit, technically you're in free fall because the only forces that are acting on you are the forces due to gravity. The idea of being weightless tends to stem from the idea that, oh, you're just floating there, right? So gravity's not pulling on you because you're floating, and if gravity were pulling on you, then you'd be falling. But you are falling. The entire time you're falling. Any object that is in orbit is constantly falling. It's just moving so fast horizontally or tangent to the circle, because we have some circular motion that comes back here. Because its tangential velocity is so fast, as it falls, it doesn't get pulled in. So the satellite is falling. If an astronaut is in there, the astronaut is falling. And because those two are falling at the same rate, the object can't support the astronaut, so they both just fall together, right? It would be a similar idea if an elevator, if the cables were to suddenly break and you free fall in an elevator, you would experience weightlessness there because you're falling at the exact same rate as everything around you. It doesn't support you anymore, right? You don't feel the bottom of the elevator anymore. Same idea with a satellite in orbit. Because it is falling, it still has that gravitational pull acting on it because you're really not that far away from the surface of the planet if you're in a satellite. And besides, the moon is attracted to the Earth due to gravitational forces. So the idea that gravitational forces can pull the Earth and the moon, but don't pull the Earth and like the International Space Station or the Hubble telescope, right, or any of the communication satellites that we have in near Earth orbit would be ridiculous, right? So weightlessness, you still have gravity acting on it, but there's nothing to oppose it. So you're constantly in free fall. I'll link this video in with the video lesson so that you guys should watch that and make sure you understand what's happening there as well. It gives good visual representation of weightlessness. Now, with our orbital velocity, all right, so kind of going back to Newton's thought experiment on the mountain, what we know is the universal law of gravitation. So at this point, we have the gravitational attraction between two objects divided by the square of that orbital distance. And again, that is center of mass to center of mass. That is not from the planet surface out to where the orbit is. It's from the center of that planet itself. And we know our centripetal force formula, mv squared over r, because our satellite is going to be moving in a near circular orbit more often than not, which means that the centripetal force is actually going to be equivalent to that gravitational force that's acting. So we can set the universal law of gravitation equal to our centripetal force formula, and again, the mass of the object cancels out. It doesn't matter again. The only significant piece is going to be the mass of the object that is being orbited, the planet, the star, the person, right? It doesn't really matter, right? You're going to see that the mass of that planet matters, and then the radius of that orbit, right? So how far away they are from center to center. And again, this is considered a radius because as that object is in orbit, it's going to move in a near circle. We consider it to be a circle. So technically from the center mass of the planet out to the satellite, it sweeps a circle. So we consider that the radius is what we do there. And again, this just comes down to setting gravitational law or universal law of gravitation and the centripetal force formula equal to each other and then solving for the velocity. And that's going to be our orbital velocity. So if an object were on Earth's surface, how fast would it need to move in order to maintain orbit at the surface? Not off the surface, not on top of a mountain, but on the surface. How fast would it need to be traveling? So what we know is big G. We always know big G. We know the mass of what is being orbited. That would be the Earth. And we know the radius of the Earth. And because we're maintaining orbit at the surface, the radius of the Earth is going to be the radius of the orbit. So we take our orbital velocity formula, square root of big G times the mass of the Earth divided by the radius of the Earth in this case. So we get our 6.67 times 10 to the negative 11th times the mass of the Earth divided by the radius of the Earth to get an orbital velocity of 7,910 meters per second. Again, this just comes down to using big G, the mass of the object being orbited, which is Earth, and the radius of the orbit, which in this situation is going to be the radius of the Earth. Now, another idea, the escape velocity is what this last one is here. So what the escape velocity is, if you were to move fast enough, and we saw it in that little applet for Newton's mountain, at some point you can move fast enough that you're not going to be pulled back, that your speed is going to be fast enough that the gravitational pull can't pull you back. And what that is going to be dependent on is almost the exact same as the orbital velocity. Note the difference is just the 2 underneath that square root. We're still looking at the mass of the object being orbited. We're still looking at the radius of that orbit itself. But in this case, the radius of the planet. But now, right, we have this 2 in there because our escape velocity has to be higher than our orbital velocity. So if an object is going to escape from Earth's surface, how fast is this going to be moving now? And what we can do is use our exact same set of givens, except now, right, we want to know how fast to escape Earth's surface, so the radius of the Earth is actually going to be prevalent here. So our escape velocity, 2g times the mass of the Earth divided by the radius. It's the exact same process, except we just have that 2 underneath the square root. So our escape velocity is going to be roughly 11,200 meters per second. Not substantially faster, not quite 2 times faster. You're going to want to say, oh, it's going to be twice as fast because you see that 2 underneath the square root. But remember, that's the square root of 2, not just a straight 2. So the escape velocity is not double the orbital velocity. It's actually the orbital velocity times the square root of 2. So if you know your orbital velocity, you can multiply it by radical 2 to get your escape velocity. Same thing, if you know escape velocity, you can divide it by the square root of 2 to get your orbital velocity. Right? That ends up being a nice little equality that we like to see here. Right, last idea deals with the escape velocity for a black hole. Right? So a black hole in very, very, very short terms, a black hole is a star that has collapsed in on itself to have a very, very high amount of mass in a very, very, very small area. Right? It is exceptionally dense, and because it has such a high density, once light gets within it, that light cannot escape as far as we understand, because the escape velocity is greater than the speed of light, which is 3 times 10 to the 8th meters per second. Once it gets inside of that event horizon, it's sucked in, and as far as we know, it stays there, right? We haven't been inside a black hole. We don't know exactly what it would end up being. There are plenty of theories out there. But the escape velocity for light, because we can't see into a black hole, tells us that once the light gets there, that light isn't coming back as far as we currently understand. So if we apply our escape velocity to a black hole, and let's say that our sun, which has a mass of 1.99 times 10 to the 30th kilograms, collapsed into a black hole, what would the new radius of the sun be? Right? How large would the sun actually end up being? So we use now the escape velocity, which is going to be the speed of light, 3 times 10 to the 8th meters per second. We have the mass of the sun given to us, and we have the universal gravitational constant, big G, as well given. So we're going to use our escape velocity formula, rearrange it to solve for the radius of the sun. So we're going to square everything, and then we're going to do a cross multiply and divide. Right? So we're going to square it to get the escape velocity squared. We're going to multiply the radius of the sun over, and then we're going to divide that escape velocity squared. So we plug in our values. Right? So we get 2 times big G times the mass of the sun divided by the square of the escape velocity, which will be the speed of light. And we find that the radius of the sun would be 2,950 meters. The radius, roughly 3,000 meters. That is 3 kilometers. When people run cross-country races, they tend to run less than or slightly more than that, right? Not much more, depending if they're running a 5K or not. Right? If you run a 5K, that's going to be almost the diameter of the sun. To put this number in perspective for the radius of the sun, right, with this being 3,000 meters, that is just under 2 miles for its radius, which is roughly Egan High School to where 35E is. Roughly. The entire diameter of the sun would be able to fit between Highway 3 on the far east side of Egan and between Highway 13 on the west side of Egan getting towards Burnsville. The entire sun's diameter would be able to fit in that area. The sun would be smaller than the city of Egan, but maintain its exact same mass. That is a huge amount of density, which is why its gravitational pull is so strong, thus why light can't get out as far as we understand. So here we get a little bit on escape velocities, orbital velocities, and how we can really tie circular motion into orbital velocity to be able to see that connection between circular motion and gravitation. Again, this is where we really start to see the applications of our gravitation and our planetary motion. Thanks, guys.